So in this video, we're going to see a very cute example of a little scenario where potentially coherent attacks appear to be much more powerful than collective attacks. So this scenario is not quite, QKD protocol, it's a bit more specific, but it's going to be framed as a non-local game. So let me first describe the game to you. It's a bit of a strange game, but it's interesting. So there's Alice and Bob as usual. Alice and Bob are provided inputs, X and Y, which are just bits chosen uniformly at random. So X is a random bit in 0, 1, and Y is a random bit in 0, 1. And now Alice and Bob as outputs have to produce not bits, but pairs, A and B, and these pairs are supposed to be labeled by the name of a player, Alice or Bob, and a bit. So for example, Alice on her input could say something like Bob 0, or she could say something like Alice 1, something like this, right? So instead of Alice and Bob, I wrote A and B here. And the goal, you win the game if the two players say the same thing and this thing is true. So for instance, let's do an example. Let's imagine that Alice is given a 0 as input and Bob is given a 1 as input. Then what are valid answers? So both players should say the same thing, always, and they should say either Alice 0, because this is a true statement in the sense that Alice got a 0 as input, or they could say Bob 1, because that's also a true statement. So if they say any of these two things, both of them say the same, then they win. If they say something else, then they lose. So what's the maximum winning probability in this game? Well, the thing is, each player knows their own input, but they have no idea what the other player's inputs is, right? So a valid strategy, of course, they're going to decide beforehand that they always talk about Alice or they always talk about Bob, because if they talk about different players, each of them, then they'll fail for sure. So let's say they agree on always talking about Alice. Then it means that both of them have to guess Alice's input. Now Alice can do that, but Bob has no idea. He can only guess at random. So the best success probability that you can have in this game is a half. That's for classical strategies, and for the time being I'm going to focus completely on classical strategies. There is no quantum here. Think of just classical players. So maximum winning probability is a half. Now let's repeat this game. Let's play it twice. But let's play it in parallel. Meaning that let's imagine that Alice is not only given X, but she's also given some X prime in 0, 1, chosen independently from X. Bob is given some Y prime, and they have to produce outputs A and A prime, B and B prime, and I'm going to check these outputs independently. So I'll check that A and B are valid with respect to X and Y, and I'll also check that A prime and B prime are valid with respect to X prime and Y prime. So then, okay, you have to play the same game twice. If your maximum winning probability for one round of the game was a half, then the maximum winning probability for two copies, let's call it P win 2, this should be equal to a half times a half, so it should be equal to a quarter, right? That would be the case if we restricted the players to so-called collective attacks. If we ask them to play each of the two executions of the game independently, then they'll win each of them with probability a half. I'll multiply, I get a quarter. But now let's allow them so-called coherent attacks, meaning that they get both of their inputs and they have to produce two outputs, but the way they're produced is up to them. So here's a strategy that they can play. Alice will always say AX for her first answer, and for her second answer, she'll say BX. And Bob, for his first answer, will always say A Y prime, and for his second answer, will say B Y prime. Alright, so that's their answers. Now suppose X is equal to Y prime, okay? Alice's first input is equal to Bob's second input. Well, if X is equal to Y prime, then these two match, and they're correct, because Alice's input was an X in the first execution of the game, and these two also match, and they're correct, because it's true that Bob's input in the second game was Y prime. So if X is equal to Y prime, then they win. If it's not, then you can check that they lose. But what's the chance that X is equal to Y prime? X is a random bit, Y prime is a random bit, probability half, they're equal. So we get a winning probability for this repeated game, which is a half, not a quarter, as we thought before. So in this case, coherent attacks are much better than collective attacks. Now there's some important differences between this scenario and the one in QKD. One difference is that in QKD we're talking about quantum, but in fact you can give another variant of this game, and you'll see this in the problem set, where you allow quantum strategies, and again, you have the exact same phenomenon that appears. The most important difference, rather, is that in QKD, things are being performed sequentially. And here, I allowed the players to see both of their outputs at the same time. They didn't have to produce their first output before seeing the second input. And that restriction is important. If I made the restriction here, then again I would observe that the winning probability of the game played twice sequentially is at most a quarter and not a half. And this is probably the most important thing that we're using when we're reducing the security of QKD against coherent attacks to security against collective attacks. Nevertheless, I wanted to show you this example because it shows you that some quite surprising things can happen when you don't assume independence anymore, and it's important to keep this in mind. You have to be a little bit careful.